Okay, let's jump right in. What you're looking at here gets right to the heart of it. This isn't just some random piece of industrial equipment. This is the tube bundle, and it's the absolute core of a shell and tube heat exchanger. This is the component that does all the heavy lifting in what is truly one of the most critical pieces of hardware in modern industry.
So these things, they are the absolute workhorses of heat transfer. You will find them everywhere, from giant oil refineries to power generation plants, and their job is to solve a really fundamental engineering problem. How do you efficiently move a massive amount of heat between two different fluids without them ever mixing? And you have to do this under some pretty brutal conditions. We're talking high pressures and high temperatures that would just destroy lesser equipment.
You know, the core concept is actually beautiful in its simplicity. Think of it this way. You've got this big pressure vessel. That's the shell. And packed inside is that bundle of tubes we just saw. One fluid passes through all those tiny tubes, and a second different fluid flows over the outside of them, all contained within that shell. The heat naturally moves from the hotter fluid to the colder one, right through the metal walls of the tubes. The fluids never touch.
All right, so to really get how this thing operates, we've got to pop the hood and look at the key parts that make up this incredibly robust piece of machinery.
And this cutaway view is perfect for that. You can clearly see the main players here. You've got the outer shell, the tube bundle sitting right inside, this thick plate called the tube sheet that holds it all together, and these dividers, which are the baffles. Then at each end, you have the channels, which are basically there to direct the fluid where it needs to go. Let's zoom in on a couple of these.
Okay, let's start with the tube sheet. Now, this heavy-duty plate of metal, you could argue it's one of the single most critical components for keeping the whole operation safe and reliable. Its main job is to hold all those tubes securely, but more importantly, it's the absolute firewall. It's the primary barrier that makes sure the stuff in the tubes and the stuff outside the tubes stay completely separate. No leaks, no mixing, period. Now, these things are fascinating. They're called baffles, and they might look like simple dividers, but they're doing two incredibly important jobs at once. First, they provide mechanical support. Without them, the tubes could actually vibrate themselves to failure. It's a real phenomenon. And second, they force the fluid on the shell side to take this zigzag path across the tubes. That creates a lot of turbulence, which, just massively cranks up how efficiently the heat can transfer.
Okay, so we've looked at the hardware, the static components. Now let's get things moving. Let's trace how the fluids actually flow through this thing, because that's where the magic really happens. This diagram lays it all out beautifully. You can see two totally separate circuits. First, let's trace the tube side fluid, the blue path. See how it comes in one end, flows through a whole set of tubes, hits the back, and then gets turned around to flow through another set before heading out? That's what we call a multi-pass design. At the same time, you've got the shell side fluid, the red path, coming in through a nozzle up top. The baffles force it to snake back and forth across the tubes before it finally exits at the bottom.
And the direction those fluids are flowing, that's not random. It's a really critical design choice. You could have co-current flow, where they both travel in the same general direction, but the most efficient setup is usually countercurrent, where they flow in opposite directions. By doing that, you maintain a more consistent temperature difference between the hot and cold fluids all the way through the exchanger, and that means you're wringing out the most heat transfer possible. It's just way more efficient.
But here's the thing. You don't just bolt one of these together from a kit. The design is all about anticipating problems. Every single choice, from the metal you use to how it's built, is dictated by the tough, real-world conditions it's going to face out in the plant.
And these are the big ones, the key things an engineer has to juggle. What material do we pick to resist corrosion? How do we account for thermal expansion so the whole thing doesn't tear itself apart? How fast is gunk, we call it fouling in the industry, going to build up on the tubes and kill performance? And what about the pressure drop? Too much and your pumping costs go through the roof. Every single one of these shapes the final design.
And this quote right here, it hits the nail on the head when it comes to materials. In a lot of plants, you're dealing with sour service. That's a fluid with corrosive sulfur compounds in it. If you used plain old carbon steel, it would get eaten alive. That's exactly why the design codes and standards demand you use high-end materials. Things like stainless steel or special nickel alloys, because they're built to survive in that kind of nasty environment for years and years.
It's exactly that focus on bulletproof design that makes these exchangers the go-to choice in so many critical industries. Their reliability isn't a happy accident. It is engineered right in from the very beginning to ensure a long, predictable life.
And believe me, you see them everywhere. Oil and gas, They need the sheer strength to handle insane pressures. Petrochemical plants? They need special materials to fight off corrosion from aggressive chemicals. Power generation? They're absolutely essential for condensing steam and keeping the whole cycle efficient. Heck, even in food processing for stuff like pasteurization, it's all about that precise, reliable temperature control. The basic design is just that good and that flexible.
So, this all brings us to a final question, and it's a big one that engineers wrestle with all the time. For a critical piece of equipment like this, what's going to have a bigger impact on its long-term reliability? Is it spending the big bucks up front on the absolute best, most bulletproof materials you can find? Or is it being incredibly disciplined about your cleaning and maintenance schedule over the decades it's in service? It's that classic engineering trade-off, initial investment versus operational discipline. And that really gets to the core challenge of industrial reliability.